Welcome students. So let's see this problem. Each of the two uniform hinged bars have mass m and length L each and is supported and loaded as shown in the figure. For a given force P, determine the angle theta for equilibrium. This is a case of equilibrium. Now there is one way to solve this problem, that balance force and balance torque. But for the system, if you want to balance force and torque, it can't be done because there will be lesser number of equations than the variables that has to be solved. One other way is to draw this bar separately and this bar separately. There are force here, this force will be P, and same here, this force here, same, that will be same as P. This is normal reaction, and this. Okay, so that's actually a long process. So we don't want to take that long route here in this problem. Rather, we will solve here by the principle of virtual work. And you know, the principle of virtual work is that if a system is in equilibrium, then the work done by the active forces. Now, what are the active forces? That's the forces capable of doing work. If a system is in equilibrium, then work done by the active forces due to the virtual displacements. See, the virtual displacement will be as per the constraints of the system. Is equal to 0. So this is the principle of virtual work, that if a system is in equilibrium, then work done by the active forces due to virtual displacements as per the constraint of the system is equal to 0. That means if the forces, suppose there are forces acting on the body, so F1 plus F2 plus F3 up to Fn, their sum is equal to 0. So if you dot product displacement with these forces, then also you will get 0. That's the principle of virtual work in a nutshell. But here let's see what are the active forces. See, if you look at the forces, there are many. The forces can be this forces at the hinge, normal reaction here, the forces at this hinge, but neither of the forces at this hinge and neither the normal reaction here are capable of doing work. So the forces capable of doing work are P and the weight mg. So there will be weight of each bar is equal to mg. Now virtual displacement, by that we mean that if the virtual displacement occurs, then it will be like this, right? Okay. That means the point P will move further to the right, and the bars, center of gravity of the bars will go up a little. Okay. Now let's equate the virtual displacements. Let us find out the virtual displacements. Now this weight is equal to mg, both the weights are equal to mg. Now we can regard this as x and so this as, say this is y. Okay, this is y. So that's why again, because center of gravity is at the midpoint, we know. And from the simple triangle, this right angle triangle, you know this angle is theta by 2. So you know x by 2. So x, or rather you can write x equal to 2l times sine theta by 2, and y, or rather 2y, is equal to L cos theta by 2. So that means y is equal to L by 2 times cos theta by 2. Now this small displacement downward will be dy for both dy, and this small displacement will be obviously dx. Now let's find out dx and dy. So dx equal to 2L cos theta by 2 into theta by 2 multiplied by d theta. Now same way dy is equal to minus of L by 2 sine theta by 2 times add this won't come na, 2L cos theta by 2, so some half will come, yeah, half. So here also a half, so again this half will come times d theta, right. So now now the virtual work, the net virtual work is equal to 0. That means it is p dx, p times dx and dy. So plus mg times dy, and that multiplied by 2 is equal to 0. So therefore p times dx is L cos theta by 2 d theta, and there minus 2 mg at dy, L there it is L by 4, right, L by 4 sine theta by 2. So that's equal to 0. Now therefore we can write tan of theta by 2, tan of theta by 2 is 2 will cancel out, L will cancel out, or tan theta by 2 is 2p divided by mg. So therefore theta is equal to tan inverse of or rather twice tan inverse of 2p divided by mg.